Hi students. In this lecture, I am going to discuss problems based on pressure and force. Let us see first one. See the question given. A liquid of density rho is filled in a conical vessel with its base on a horizontal surface. Force by liquid on curved surface is. Let us see how to start. So it is given that a conical, it is a cone. Liquid is now filled. Now liquid is inside. Right, we can see here, see the question given. We have to find force by liquid, force exerted by liquid on curved part of the surface, right? On curved part. So it is just like the previous question. Now consider equilibrium of the liquid. So we are knowing that liquid takes the shape of the vessel. That means it is also a cone. It is also a cone. Now see free body diagram for the liquid. So forces that are acting on the liquid. One is weight mg, that is downwards. Weight mg downwards. Next, force by bottom of the cone on liquid upwards. I'm taking as F suffix B. Force by bottom of the cone on liquid upwards. Next, force by curved part. So by curved part, force is always normal to contact. So force is like this from all directions. Okay. Now you can take components along horizontal and along vertical. And by symmetry, horizontal components get cancelled. Remaining is only vertical. Now they are vertically downwards. So by curved part of the cone on liquid is vertically downwards. Net value, I'm taking it as F suffix C. Force by curved part. It is vertically downwards. So since liquid is in equilibrium, net force on that should be zero. Okay. Let us see how to calculate now force by bottom of the cone on liquid. So here we have to focus what is pressure. Okay. And pressure equal to, if you assume that at the top means at this point pressure equal to zero. Assumption one, here pressure equal to zero at the top. Okay. In that case, at the bottom, pressure equal to H rho G. It is H rho G. So it is now H rho G. That is pressure. Pressure into area. Area equal to, it is a pi r square. Right. So here we have taken one assumption that at this point pressure equal to zero. Then at the base, pressure equal to H rho G. That pressure into area, that is a pi r square. This is a force by liquid on the bottom of the cone, or you can say by bottom of the cone on liquid. Okay. Next, now focus weight of the liquid. So weight equal to, weight equal to See what is volume. Volume equal to, it is 1/3 pi r square h. This is volume. Volume of liquid into density. That is mass of liquid into g. That is weight of the liquid. Right? Now from this we can say force by curved surface of the cone. Right? So Fc is equal to Fb minus weight of the liquid. See how much we get. This is h rho g into pi r square. This is h rho g into pi r square by 3. So remaining is now how much? 1 minus 1 by 3. It is 2 by 3. So 2 by 3 pi r square into h rho g. This is now force by curved surface of the cone. So here you have to keep one point in mind, that is at this point we have taken assumption pressure equal to 0. Okay, in that case this is our answer. Okay, so this is almost same as the previous problems, right? Let us see the next problem. So in this our answer is, it is option C, right? Option C is the correct one. Let us see next one. The density of a liquid varies with the depth as rho equal to k into h. So here h stands for depth. Find the pressure P as a function of h if P naught is the atmospheric pressure. So in this case, density is not same everywhere. It is changing with the depth, and that is given. Let us see how to finding pressure. So it is given density as a function of depth. So it is given as k into h, rho equal to k into h. Suppose this is now surface of liquid. Surface. We have to find pressure as a function of depth. Let us see what we have to do. Consider a cylinder. Consider a cylinder of length h. Its length equal to h. Okay. Now we have to focus how to calculate pressure. Say we have learned that pressure is defined as normal force per unit area, right? Suppose now this area equal to dA. Okay. So force acting on this base. See how much. Again, here we are taking the same concept. Consider this part of the liquid. Okay. Now this part of the liquid is in equilibrium. So we are just imagining a cylinder. Remember, physically there is no cylinder is present. We are just imagining one cylindrical shape. Now, a liquid in this cylinder is in equilibrium. Then net force on that liquid must be equal to 0. Okay. Then see number of forces that are acting on liquid. So first thing, weight mg, it is vertical downwards. Next, force because of pressure of atmosphere. That is a P naught into dA. P naught into dA. That is also downwards. So plus P naught into dA. Next, by curved part. That means by surrounding liquid, force is only along horizontal. and that will get cancelled. Okay. Next, by bottom means by liquid on the bottom, we can say force will be vertically upwards, and that is equal to pressure at that point into corresponding area. So force by this part of the liquid on this liquid is upwards. That is a P into A. So this is a P value which we want to calculate, right? So to know this value, first we should know what is mg, right? Now see how to get mg value. So here what I am doing is I am taking now at a depth h, at a depth h. So take a layer of thickness dh. Okay, layer of thickness dh. Now we focus what is weight of this layer. Okay, then we take sum of the weights of all these layers. Sum of the weights of all these layers. That gives weight of the liquid. Okay, see how to get it. So it is now volume of that layer. Volume equal to area is dA. So dA into this thickness is now dH. This is now volume of that layer into density. Density given as K into H. So this is volume into density. This gives us mass of that layer, right? Into G. That is now weight of that layer. And students, you should remember here one point. We are taking assumption that this depth is very small, so that G is a constant. So we have learned in gravitation that G changes with the depth. I'm writing here with the depth G value, G on surface into 1 minus H by R. So G changes with the depth. But here we are taking the assumption that this depth is very small, so that G is a constant. Okay. So it is now cross check once, area into its thickness, that is volume, into density, that is mass, into G, that is weight of that layer. Like this, we have take all layers from H equal to 0 to up to H. Okay. From H equal to 0 to up to H. This gives us weight of the cylinder. Okay. See how much? You can take constants outside. dA, take outside G and K outside. dA, K and G outside. HDH. It is now H square by 2. Now taking limits. Okay. This is weight of the liquid present in the cylinder. Okay. Now substitute that here. So here what we get? mg plus P naught dA is equal to P naught, sorry, it is P. It is P into dA. It is P into dA, right? So from that P equal to P naught plus mg by dA. And mg value we got here by dA. We get k h square by 2. This is a P naught plus k g h square by 2. This is now pressure as a function of h. Okay. So we have to focus in mind how we are calculating. So first we are calculating weight of the liquid that is present in the cylinder. Okay. And here we have taken assumption that here depth is very small, so that G is a constant. If depth is not small, then we cannot take that assumption. Then we have taken the place of G. H equal to G into 1 minus H by R. Okay. Let us see next one. The density of air in Earth's atmosphere decreases with height as rho equal to rho naught e power minus kh, where rho naught is the density of air at sea level and k is a constant. K is a constant. The atmospheric pressure at sea level is, and here given, I assume that acceleration due to gravity does not change with the height. So assumption is already given. In the previous problem, we have taken assumption with the depth G not changing. We have taken that H is very small. So here assumption already given. Right. So both are almost same kind of problems. Given density as a function of height. In the previous question given as a function of depth. That is the only change. Again, here we have to calculate what is weight of the air. If you imagine one cylinder, okay? Let us see. Right. First of all, note down the given data. It is given density with a height rho equal to rho naught e power minus kh. Okay. So we have to find pressure at sea level. Right. Wait. What is given here? Rho naught is density at sea level. Atmospheric pressure at sea level is okay. So now imagine once again, we we are taking a cylinder of infinite length. We are taking now a cylinder of infinite length. Suppose now this is sea level. Okay. Suppose this area equal to dA. So again here we have to calculate weight of the air present in this cylinder. I am repeating. Here we have to calculate weight of the air present in the cylinder. That weight by this area gives us pressure. Okay. So by definition, pressure equal to normal force per unit area. So here normal force is nothing but weight of the air, right? Which is vertically downwards. Now see, so we are taking at a height h, consider a layer of thickness dh, a layer of thickness dh. So calculation almost same as the previous problem. Okay, so dh. Now see what is weight of this layer. What is weight of this layer? Remember, here also with the height g value changes. So we have learned in gravitation with the height g value g into r by r plus h whole square. So g changes with the height. But here assumption given that I assume it is a constant. Okay. So here weight of this layer. So first focus volume dH into dA. That is now volume of this layer. Okay. Volume of the air present in this layer. dH into dA. Volume into density. Density is now rho naught e power minus kh. Area into that height, volume into density, that is mass into g. This is weight of the air present in that layer. Like this, we have to take all layers from h equal to 0 to up to infinity. What is it? Up to infinity. Okay. Then we get weight of the air present in that cylinder. Okay. So it is now from h equal to 0 to infinity. That is giving us weight of the air present in that cylinder. See how much we get. We can take a constants outside. So rho naught g dA taking outside. Remaining is now dH e power minus kh. So e power minus kh into dH. Now see calculation rho naught g dA integration of this. It is e power minus kh upon minus k, right? Limits 0 to infinity. Let's see what we get here. And I'm calculating directly mg upon dA because that is what we want to calculate. So pressure P at sea level is equal to mg upon dA, normal force per unit area, right? That is equal to rho naught here. What we are having rho naught g. Now substitute limits, we're having minus k. If you are taking it infinity, that becomes a 0, right? Infinity. And if you are taking 0, e power 0, that becomes 1, right? It becomes now 0 minus, it is 1 by minus k, right? So that is equal to rho naught g upon k. That is now pressure at sea level. Okay. And students, remember here, suppose if we are not given the assumption that G is a constant, if that assumption is not given, then we have to take this value in the place of G. It is G into R by R plus H whole square. Then we have to make the calculation. Okay.